Welcome dear learners. We are continuing quantum chemistry and in this module we are discussing Huckel molecular orbital theory or HMO theory. The contents of this module are HMO theory, overlap integral, Hamiltonian integral, Huckel's approximations, secular determinant and applications of HMO theory to ethylene molecule. First of all, Huckel molecular orbital theory. The Huckel molecular orbital theory is a simplified quantum mechanical approach used to predict the electronic structure and properties of conjugated organic molecules. What are conjugated organic molecules? These are the molecules in which alternate single and double bonds are present. For example, if you are taking 1,3-butadiene, it can be considered as a conjugated molecule. Benzene is a cyclic conjugated molecule. 1,3,5-hexatriene is another conjugated molecule. In such systems, based on Huckel molecular orbital theory, it is easy to apply the Schrodinger wave equation and to get the resultant solutions to find out the electronic structure as well as energy states of the system. And the HMO theory was developed by Erich Huckel in the year 1930. The HMO theory is primarily applied to conjugated systems where a series of alternating single and double bonds are present. The double bond means pi bonds and they form a continuous system of p orbitals. Hence, this HMO theory is highly applicable to conjugated systems and conjugated organic molecules. This theory predicts the distribution of pi electrons in a molecule by forming molecular orbitals. And such molecular orbitals are termed as Huckel molecular orbitals. In the Huckel approach, the molecular orbitals are constructed from linear combination of atomic p orbital wave functions on carbon atom which are involved in the conjugated system. And this is the expression for making Huckel molecular orbital. The ith Huckel molecular orbital psi I is equal to sigma j is equal to 1 to j is equal to n Cij phi j, where I is equal to 1, 2, 3 etc. up to n, where n represents maximum number of pi electrons present in the system. For example, if you are having 1,3-butadiene, it is a 2 double bonded system or it is a 4 pi electron system. For such a system, n is equal to 4 and this value is j is equal to 1 to 4 Cij phi j up to phi 4 we have to take the values, and this phi j is the 2p Z orbital centered on carbon atom j. Here in this expression for Huckel molecular orbital, the phi's are termed as the basis set. The overlapping of n 2p Z orbitals present on each carbon atom leads to the formation of n pi molecular orbitals. That is, the overlapping of n 2p Z orbital leads to the generation of n pi molecular orbitals. For instance, if you are taking 1,3-butadiene, there are 4 2p Z orbitals. They will overlap together to produce 4 Huckel molecular orbitals. We will discuss it later, and that Huckel molecular orbitals are depicted or designated as psi 1, psi 2, psi 3 and psi 4 in the case of 1,3-butadiene. The Huckel molecular orbital theory is commonly used to predict the electronic structure, stability and reactivity of aromatic and conjugated organic molecules. It is highly valuable for understanding the properties of aromatic hydrocarbons and for predicting UV visible absorption spectra of these compounds. Hence, this HMO theory is a highly useful concept. First of all, we are discussing, before entering into the HMO theory, first of all, we are discussing about an integral that is termed as the overlap integral. The overlap integral is used to quantify the overlap of atomic or molecular orbitals. By definition, overlap integral is Sij equal to integral phi I star phi j d tau. Here phi I and phi j are two orbital wave functions. Phi I star represents the complex conjugate of the wave function phi I, and if we are dealing with the real function phi I star same as phi I, therefore this equation can be changed to Sij equal to integral phi I phi j d tau, and this Sij is termed as overlap integral. It should be noted that the overlap integral Sij represents the extent of overlap of orbitals phi I and phi j centered on atoms I and j. This overlap integral is highly important as far as HMO theory is concerned. Now we can move on to some details of the overlap integral. Here Sij equal to integral phi I phi j d tau. If both are same, then I can represent as Sii phi I d tau. As per the condition for normalization, we know based on the quantum mechanical postulate, a function must be normalized. The condition for normalization is integral psi star RT psi of RT d tau must be equal to unity. Instead of psi star RT, here we are having phi I, and psi of RT, it is also phi I. Since we are discussing with the real functions, phi I star is same as phi I. Therefore, Sii is equal to integral phi I d tau, and that is equal to unity. This is based on the condition for normalization. And we can take several examples for the overlap integral. So let us consider S12. What is meant by S12? By definition, S12 can be represented like this: integral phi 1 star phi 2 d tau. Or if we are discussing with the real functions, phi 1 star same as phi 1. Therefore, S12 can be represented as integral phi 1 phi 2 d tau. In a similar way, we can represent SAB. SAB equal to integral phi A phi B d tau. S alpha alpha can be represented like this: integral phi alpha d tau. And S22 can be represented like this: integral phi 2 d tau. Here the first function is actually the complex conjugate, but we are discussing real functions, therefore we need not represent the star or complex conjugate sign. For real function phi I is same as phi I star. Hence, SAB equal to this one, S alpha is equal to this expression, and S22 is like this. Thus, overlap integral is a quantity that represents Sij equal to integral phi j d tau, and it is the quantification of overlap between two wave functions, namely phi I and phi j. Moving on to the second important integral, that is the part of HMO theory, and that integral is Hamiltonian integral. The name Hamiltonian integral is because of the fact that this integral consists of a total energy operator called Hamiltonian operator. Hence the name Hamiltonian integral. Then what is Hamiltonian integral? The general form of Hamiltonian integral is shown here. Hij is equal to integral phi I star h hat phi j d tau, and this h hat is called Hamiltonian operator that we learned in previous modules. Hamiltonian operator is the total energy operator. It consists of a kinetic energy part and a potential energy part, and H hat is equal to minus S cross square by 2m del square plus V. This is Hamiltonian operator. Since Hij consists of the Hamiltonian operator, Hij is termed as Hamiltonian integral. The name Hamiltonian integral is because of the fact that this integral contains Hamiltonian operator. And in this equation, if we are having real function, then phi I star can be replaced as phi I. Phi I star can be replaced as phi I. So, we can ignore this phi I star and we can simply represent Hij equal to integral phi I H hat phi j d tau, and this is for real functions because phi I is equal to phi I star for real functions. And in this Hamiltonian integral, if I not equal to j, then the Hamiltonian integral is termed as exchange integral or resonance integral. That is, it is a condition where in Hij I not equal to j. If I not equal to j, the Hamiltonian integral can be considered as exchange integral or resonance integral. And the exchange integral represents the energy of interaction of the electrons in the atoms I and j. And there is one more condition. We have the Hamiltonian integral Hij equal to phi I star H hat phi j d tau. And in this expression, if I is equal to j, then the Hamiltonian integral is termed as the Coulomb integral. The Coulomb integral represents the energy of interaction of electrons in the atomic orbital centered on atom I. Thus, we have the overlap integral and Hamiltonian integral. Hamiltonian integral consists of Hamiltonian operator and it is marked as Hij. Hij equal to integral phi I H hat phi j d tau. If I is equal to j, it is termed as Coulomb integral. If I not equal to j, it is termed as resonance integral or exchange integral. Now, we are discussing Huckel's approximations. Huckel takes several assumptions and approximations to evaluate the so-called overlap integral and Hamiltonian integral. Such approximations make solving of the Schrodinger wave equation more easy. That is, it is possible to apply Schrodinger wave equation very easily based on approximations put forward by Erich Huckel. And we are now focusing on Huckel's approximations. Huckel made the following assumptions about three kinds of integrals: Coulomb integral, exchange or resonance integral, and overlap integral. We previously learned that the first two integrals are generally known as the Hamiltonian integral. So, Huckel put forward some approximations to find out the value or to simplify the secular equation which is a part of Huckel molecular orbital theory. And these are the Huckel's approximations. It is very important. Hij is termed as alpha provided I is equal to j, that is Coulomb integral. It means that if you are seeing a Coulomb integral that is I is equal to j, we can put its value as alpha. Then Hij is taken as beta if it is an exchange integral. Moreover, there must be a connection between I and j. The connection is that I equal to j plus or minus 1. That is, there is one unit difference between I and j. In such a case, Hij is taken as beta. However, if the difference is greater than 1, that means I not equal to j plus or minus 1, Hij is equal to 0. And in the case of overlap integral, these are the two assumptions. The assumptions are Sij equal to 0 if I not equal to j, and Sij equal to 1 if I is equal to j. So, these 5 expressions are important Huckel's approximations which helps us to solve secular equation more easily. Once again, Hij equal to alpha, provided I is equal to j, Hij is equal to beta if I is equal to j plus or minus 1, Hij is equal to 0 if I not equal to j plus or minus 1, Sij is equal to 0 if I not equal to j, and Sjj is equal to 1 if I is equal to j. Now we can take some examples for various overlap integral, exchange integral, and Coulomb integral. Now let us consider, based on this we can take some examples. What would be the value of H12? H12. This is Hij and 1 and 2. I and j are 1 and 2 respectively. If I is equal to j plus or minus 1, then the value will be beta. So no doubt H12 should be equal to beta. H11 equal to alpha, that is a Coulomb integral. That is I is equal to j. H22 again equal to alpha. Hii is taken as alpha. Hjj is taken as alpha. Here in this case I is equal to j, hence the value is equal to alpha. If I am taking H34, its value is also taken as beta, because there is a difference between 1 unit. I and j differ by 1 unit, and this is H23. H23 also equal to beta because 2 and 3, I and j differ by 1 unit. These are some examples for Hamiltonian integrals where we put Huckel's approximations. And now take some examples for the overlap integral and S12. Definitely, no doubt, S12 is equal to 0. This is because Sij, in Sij, I not equal to j, 1 not equal to 2. So, I not equal to j, hence Sij is taken as 0. So, S12 is equal to 0. But S11 equal to 1, S22 equal to 1, SAA equal to 1, SBB equal to 1, but SAB equal to 0. All these are based on Huckel's approximations where Sij equal to 0 if I not equal to j, and Sij equal to 1 if I is equal to j. All these approximations are highly useful, and we have to apply these approximations while we are solving the secular determinant in HMO theory. Now, the concept of secular determinant. The HMO theory is similar to molecular orbital theory of homonuclear diatomic molecules. We learned in the molecular orbital theory that atomic orbitals undergo linear combination to produce molecular orbitals. In the HMO theory, the basis functions are typically the 2pz atomic orbitals situated on each carbon atoms. For a system consists of n pi electrons, a secular determinant of order n by n should set first. This is the first stage of HMO theory application to conjugated systems. The n by n secular determinant is of the form H11 minus S11E, H12 minus S12E, etc. up to H11 minus S11E. H21 minus S21E, H22 minus S22E, H23 minus H23E, and the second line ends as H2n minus S2nE. Similarly, if you are taking the last line of this determinant, it is HN1 minus SN1E, HN2 minus SN2E, etc. And the last element is HNN minus SNN into E. And this determinant theoretically equal to 0, and this is the n by n secular determinant, where n represents the number of pi electrons present in the system. If we are having n pi electrons, we have to set n by n secular determinant. For example, if you are taking ethylene, it is a 2 pi electron system. So this is reduced to 2 by 2 secular determinant. For benzene, there are 6 pi electrons, so we have to set a 6 by 6 secular determinant. Like that, the secular determinant needs to be solved based on the Huckel's approximations that we discussed just earlier. On applying Huckel's approximations, the above secular equation takes the form alpha minus E beta 0 0, beta alpha minus E beta 0 0, and this is the form of the parent secular determinant only after putting Huckel's approximation on overlap integral as well as Hamiltonian integral. Now, to further solve this secular determinant, we are taking the assumption that alpha minus E by beta is equal to x, and this alpha minus E by beta is obtained by dividing each element in this secular determinant by beta. So, to solve this secular determinant further, first of all, we have to divide each element of this determinant by beta and put the substitution alpha minus E by beta is equal to x, and x is a dimensionless parameter. So, we have to divide it with the beta first, each element by beta first, then put alpha minus E by beta as x. So, this determinant takes the new form x1 0 0 0, 1x1 0 0, like that. It is interesting to note the fact that the diagonal elements of this n by n determinant are x, where x is equal to alpha minus E by beta. On solving this equation, we get the energy as well as the wave functions corresponds to HMO of the system. Now, we are focusing on application of HMO theory to some simple systems. First of all, we are taking ethylene as an example, or we are discussing application of HMO theory to ethylene molecule. We know ethylene can be considered as a simplest molecule with one pi bond, that is 2 pi electron system. This organic molecule ethylene CH2 double bond CH2 consists of one pi bond, that is it is a 2 pi electron system. So, as per Huckel's method, n number of pi electron is equal to 2, and we have to begin the HMO theory by setting out a 2 by 2 secular determinant, and that secular determinant has to be solved to get the expression for energy as well as the expression for wave function of Huckel's molecular orbitals. And we can set the HMO theory for ethylene molecule by setting out the determinant first. The determinant should be like this: H11 minus ES11, H12 minus ES12, H21 minus ES21, H22 minus ES22 equal to 0. So, this is the original form of 2 by 2 secular determinant, and we have to make assumptions or approximations based on Huckel's rule. Based on the approximations, H11 is equal to alpha minus E into S11 equal to 1. So, this element is alpha minus E, and the second term H12 is equal to beta minus E into S12 is equal to 0. So, this term vanishes. Coming to the next line, H21 is taken as beta minus ES21, S21 is equal to 0. So this term vanish. So this term changed it to beta. And this one H22 that is equal to alpha minus ES22. S22 as per Huckel's approximation, S22 is equal to 1. Therefore, E into S22 that is E into 1 that is simply E. So the diagonal elements are alpha minus E and alpha minus E, and this is another form. Now we have to take further simplification by dividing each element with the beta. Whenever it is divided by beta, each element must be divided by beta, and putting alpha minus E by beta is equal to x. So this determinant takes the form x, beta by beta is equal to 1, beta by beta is equal to 1, and this is equal to x. So x 1 1 x. This determinant is equal to 0. Or simply we are getting x square minus 1 is equal to 0. That is x square equal to 1, or x is equal to plus 1 or minus 1. Taking the root, we are getting two possibilities, x may be plus 1 or x may be minus 1. And by putting x is equal to plus 1 and x is equal to minus 1, we can evaluate it, we can find out two energy levels. And first of all, I can put x equal to minus 1. We know x is equal to alpha minus E by beta, that is equal to minus 1. This is case number 1, x is equal to minus 1, and in the next case we are putting x is equal to plus 1 to get two different energy levels. These two energy levels are the energy levels of two Huckel molecular orbitals of ethylene. So alpha minus E by beta is equal to minus 1, or alpha minus E is equal to minus beta, or alpha plus beta is equal to energy. This is the first value of energy. Similarly, we can put x is equal to plus 1 such that alpha minus E by beta is equal to plus 1, alpha minus E is equal to beta, or alpha minus beta is equal to energy. So we got two energy levels. One energy level is alpha plus beta and other energy level is alpha minus beta. It should be noted that the two quantities alpha and beta both are negative quantities. So the energy level alpha plus beta is actually low energy state and alpha minus beta is high energy state. So this alpha plus beta energy level can be considered as the energy of the Huckel molecular orbital psi 1, and alpha minus beta energy level is considered as energy level of Huckel molecular orbital psi 2. So in ethylene there are two molecular orbitals, two Huckel molecular orbitals, psi 1 and psi 2. Psi 1 can be considered as the bonding molecular orbital with energy alpha plus beta, and psi 2 can be considered as anti-bonding molecular orbital with energy alpha minus beta. So whenever we are applying the HMO theory by solving the secular determinant, we got two energy levels corresponds to two Huckel molecular orbitals, and the two Huckel molecular orbitals are psi 1, that is bonding molecular orbital with energy alpha plus beta, and psi 2 is the antibonding molecular orbital with energy alpha minus beta. Now this is the energy level diagram. After obtaining the energy levels of ethylene molecule, we can now plot this energy level diagram, and here we can see that alpha plus beta corresponds to the first Huckel molecular orbital psi 1, which is bonding molecular orbital, and alpha minus beta corresponds to the second Huckel molecular orbital, which is anti-bonding molecular orbital, and alpha minus beta is equal to the energy of the anti-bonding level psi 2. Since the two electrons are populated in the first level, it is considered as bonding molecular orbital, and psi 2 must be anti-bonding molecular orbital. The two electrons are present in this energy level psi 1. Now, we can make some calculations based on the above energy level diagram. It should be noted that two electrons are present in alpha plus beta energy level. The energy level diagram is simply like this. The first level, that is psi 1. Psi 1 is having an energy, that is alpha plus beta. The second energy level, that is psi 2. Psi 2 is having an energy alpha minus beta. The two electrons are present in the level alpha plus beta, or this alpha plus beta level is marked as the bonding molecular orbital level, and we have to evaluate total pi electrons energy first. What is meant by total pi electrons energy? We have to multiply number of pi electrons with its energy state. So, the two pi electrons are present in the energy level alpha plus beta. Therefore, total pi electrons energy is equal to 2 into energy of that level, that is alpha plus beta, that is 2 alpha plus 2 beta is the total pi electrons energy of this ethylene molecule. Now, we can compute another parameter, that is called energy required for excitation. Energy required for excitation can be considered as this energy difference between alpha plus beta and alpha minus beta. That is, we have to promote one of this electron to the next higher level. We are going to calculate that energy difference. So, the energy difference is higher energy minus lower energy, that is alpha minus beta minus alpha plus beta. So, you have to get the energy difference. Alpha minus alpha will vanish and you are getting minus 2 beta. Minus 2 beta is the energy required for excitation. So, by putting minus 2 beta energy, one can promote the electron present in the bonding molecular level to the anti-bonding molecular level, or simply that is considered as the HOMO-LUMO transition. So, if you are evaluating energy corresponds to minus 2 beta, then it is possible to find out a necessary wavelength used for this excitation. That all about the energy level calculation is based on HMO theory. Now, the bonding molecular orbital psi 1 and ABMO psi 2 are wave functions that are linear combinations of phi 1 and phi 2 with the different coefficients. By applying the principle of normalization and secular equations, it is possible to evaluate the values of the coefficients that may appear in the wave function psi 1 and psi 2. And the bonding molecular orbital wave function psi 1 and antibonding molecular orbital wave function psi 2 can be calculated as psi 1 equal to phi 1 plus phi 2 by root 2 and psi 2 equal to phi 1 minus phi 2 divided by root 2. That all about the present module on initial part of Huckel molecular theory and application of Huckel molecular theory to ethylene. Have a nice learning experience. Thank you.